into D9. We're going to start here. I'm going to come around the corner. All right. So for D9, we're using some of the techniques that we've learned throughout the rest of the standard to work with the graphs again, but kind of in a different way. The standard is related to the work we've done with original graphs and derivatives. However, we're not going to work exclusively with the graphs like we did before. I'm going to basically give you the function, and instead of graphing it, we're going to be able to tell things about that function based on values from the derivative. There are several types of questions in which you need to know the absolute maximum point or the absolute minimum, or whether or not a certain value is a max or min without a graph. Often they'll give you a function like this that is pretty much impossible to graph, and it'll be on a non-calculator portion, and then this is how they expect you to find the information about whether it's a max or min. So, however your answer, because we're going to be doing a sign chart here, but your answer can never just include the sign chart. You need to rephrase your findings in a statement every time or it doesn't count as an answer to the question. This is crucial on the AP test for these types of problems. So you can't just have the sign chart, but you have to basically write out what the sign chart tells you. So, start with the first step. This whole process is called the first derivative test. And basically it's just testing certain things about the function that will tell you something about the graph. So we have to start first by taking the derivative of the function. And often when we take the first derivative, we're going to take the second derivative because a lot of times they ask for concavity. Concavity is the curvature of the graph of the curve, if it's curving up or curving down at a certain value. So the second derivative is what finds that. All right, so we take the derivative of the function. We set the first derivative equal to 0 to find what we call critical points or critical values. And then we also take the second derivative and set it equal to find more critical points. Then we're going to make two sign charts. Now, ignore this. This goes with the next one. You're going to make two sign charts, and they're going to look something like this. We have a line, and then every point that you found in step 2 here, every critical point, you're just going to mark. Then you're going to test values in the first and second derivative because you're going to have two different sign charts, one to represent the first derivative, one to represent the second. But you're going to test values to left and right of the critical values to determine whether you're negative or positive. Then we're going to use symbols to show what the sign chart identifies. So when we fill out our sign chart, it'll tell us something about the function. It'll tell us where we're increasing, where we're decreasing, where we have plateau points. Remember, plateau points are not max or mins, but they're kind of places where your function is continually increasing but kind of plateaus a little bit. Where you have max or mins, where the concavity is, or what the curvature of the graph is. For example, in this curve that I just drew, this would be considered concave down because the curvature is in a downward direction. And this is where it switches to concave up. And then the last step, this isn't part of every problem, but it is, well, when we do the AP practice later for the test, often when they have you do the sign chart like this, they will ask you to find the absolute max or min. What that's asking for is, in the original function, what's the highest point you have and what's the lowest point? And they usually have to give you some sort of parameters, because most functions increase and decrease that bound eventually. So when they do ask you to do that, or when I ask you to do that, you're going to plug the critical values into your original function and your endpoints, and then the highest y value wins, basically. You're just basically creating a t-chart here in this step. But where we're going to focus our attention for this standard are these 5 steps here. Make sure we have those down, because this is just like an afterthought. We need to make sure we have this process down well. Okay. Hopefully you paused that if you needed to copy down what you needed to. All right, here's my first function. extrema is just another word that they use for max or mins, just for general reference. Alright, so we're going to start by taking the derivative. So the derivative is going to be 3x squared minus 12x plus 12. And we're also going to determine concavity, so we take the second derivative. Okay. Then we're going to set each of these functions equal to 0 to find my critical values. The critical values just mean something important is happening there, where my derivative is 0 and where my second derivative is 0. If you recall when we were doing the derivative graphs before in the last unit, where the derivative was 0 was where you had a point of inflection in the original function, because it was the steepest, or sorry, not where it was 0. Where it was 0 is where you had a max or min in the original. Where your second derivative is 0, that's going to be where you have a max or min in the derivative, and where you have a max or min in the derivative is a point of inflection in the original. So whenever you set either the original function, the derivative, or the second derivative equal to 0, the values you come up with mean something is going on with the graph at that point, the original graph. So that's why they call them critical values, because something's changing, something's moving, something's highest, lowest. There's a point of information there that's important for us to know. So this looks like I'm going to factor. If I pull out a 3, makes it a little better to factor. I get x minus 2 and x minus 2. So looks like 2. Here's my sign chart for the first derivative. This is my only critical value. So 2 is my only critical value for here. Here, if I solve, I'm going to move 12 over, divide by 6. So again, I get 2. Now, this will happen sometimes. It will not happen every time that you get the same critical value for both the first derivative and second derivative. But this is a good problem to start with. Once you take the derivative, set them equal to 0, mark out your sign charts, and for each one you're going to evaluate some value to the left and some value to the right, and you're going to plug it into the function that's assigned to the sign chart. So I'm going to plug in 0 because 0 to the left is 2. If I plug 0 into my derivative, I get 12. I'm not going to write 12. I'm going to write positive because it's a positive 12. When I plug in, let's say, 3, 3 squared is 9. 9 times 3 is 27. Well, actually, it'd probably be easier to plug it in here. 3 squared is 9. You're subtracting 12. So you have negative 3. Negative 3 plus 4 is a positive. So we end up getting a positive again. Let's try it down here. If I plug in 0, I get a negative. And if I plug in 3, I get a positive. Now, it doesn't matter what number you plug in. Just plug in an easy number to the left and an easy number to the right. Now, let's talk about what this means. What this means in my derivative, when my derivative is positive, that means my original function is increasing. So to show that, I'm going to draw an up arrow. And since we're both positive here, I'm going to have 2 up arrows. Now, this is either going to be a max, a min, or a plateau point. If this was to go from increasing to decreasing, then we would have a maximum. If it was going to go from decreasing to increasing, then we would have a minimum. But we're increasing, and we're increasing again. But here, the derivative equals 0, because that's how we found it over here, that the derivative equals 0 at 2. That means this is a plateau point. It's where it bottoms out a little bit, but the function continues to increase. I think that's all we had to go to there. Okay, so we have plateau point, increasing, increasing. Then the second derivative, where the second derivative is negative, that means we're concave down. So the curvature will be downwards. Here the curvature is going to be upwards. Where the concavity switches, or wherever the concavity switches, That point is called a point of inflection. Okay, so if you had to determine all this stuff, you would make these sign charts. This tells you something about the original graph. This graph is actually going to look a lot like the one I drew over here. You're completely increasing. You're concave down, then concave up. Because your concavity switches, you have a point of inflection. And we have a plateau point there because it kind of bottoms out. So it fits all those parameters. So we need to kind of write a statement here, or give me more information. We'd have a plateau point at x equals 2, and also at x equals 2, we have a point of inflection. Okay, so both those things are true at 2 based on this. Other things that I would expect you to say, and I'm going to have to move this way, is that your original function is increasing from negative infinity to infinity, because we didn't have any switcheroos there. We are concave down from negative infinity to 2, and concave, oh dear, sorry, concave up from 2 to infinity. Alright, so it does seem a little redundant to write down everything we can tell from the sign charts, but they do not take this as an answer, they only take this stuff as the answer, even if you have all the work that gives you that information. So I'm going to expect you to write it out too. Okay, let's look at this. Same directions. So we're going to take the first derivative. First derivative is 4x cubed minus 32. Second derivative gives me 12x squared. Then we're going to take the first derivative, set it equal to 0. Second derivative, set it equal to 0. Here when I solve, I'm going to move the 32 over, divide by 4. I end up getting x cubed equals 8. So x equals 2. Okay, we'll get away from that x equals 2 thing eventually. Here the only answer that can happen is that x equals 0. So my sign chart for f of x is going to have one critical value again. Your sign chart for the second derivative is going to have 1. But notice now they're different, but that's okay. So again, we're going to test values to the left and the right. So I'm going to test a value to the left of 2. I'm going to test 0. We have to plug it into the derivative to find out if you're increasing or decreasing. So plugging in there, I get a negative value. If I plug in 3, 3 cubed is 27. 27 times 4 is a much larger number than negative 32, so I'm going to end up having a positive. Down here, if I plug in a negative number, if I plug in any negative number, it's going to end up being positive. And if I plug in any negative number here, or positive number, sorry, it's also going to be positive. Okay. So here, what this originally tells me about my original graph is I'm decreasing, then increasing. So if I'm decreasing my original and then I'm increasing, that makes 2 a minimum. For concavity, you're concave up, you're concave up. So there's no point of inflection at 0. We would just say that's a critical value, but it doesn't affect my graph like a point of inflection would. So when you write out your answer, really the only thing here that we can say, well, there's 3 things we can say here. I'm going to start with this point at 2. We have a minimum point at x equals 2. We are concave up. from negative infinity to infinity. And we're going to say we are, I should say, f of x is decreasing from negative infinity to 2 and increasing from 2 to infinity. And that kind of summarizes everything that we see in those sign charts there. Okay, one more problem we're going to do together, and then excuse me, we'll do the 4-type problems together in class next week probably. Okay, so go ahead and write that down. All right, we're going to take the derivative of this function. Now, take the derivative of this, I have to use the quotient rule. So we have low d high minus high d low all over low squared. Let's go ahead and clean that up before I try and take the second derivative. So we have this would be 2x cubed. Oh, okay. This would be 2x cubed. This would be negative 2x cubed. So those are going to cancel out completely. Just giving you negative 18x. Excuse me. Over x squared minus 9 squared. Okay, and then f double prime. Again, quotient rule. So low d high minus high d low because we have to use the chain rule on the bottom there. All over low squared. And again, I'm going to clean it up a bit. You know what? That's going to take a little bit more to clean up then. Okay, so I'll let you know that concavity, yeah, I don't think I'd give you something that crazy to do concavity with, because we're going to end up having a lot here on top, I think. Yeah, and we're getting close on time. Draw a little thing around here. I'll probably revisit this for a review one day, but right now, to finish up this video, we'll just do the first derivative test here. So if I set this equal to 0, the great thing about having a quotient like this is normally to get rid of a quotient, we'd multiply both sides by whatever the denominator is. But because you're setting equal to 0, when you multiply both sides by x squared minus 9 squared, it cancels it completely out because 0 times this would just be 0. So you really end up just getting negative 18x equals 0, so x equals 0. Now, I should say also that all these examples have had just one critical number, but it's not uncommon to also have another critical number. So you might come across a problem where you have 0, you might have 2, or 0 and 1. That's not abnormal, so you can have more than one. If we plugged in negative numbers to the derivative here, the bottom will always be positive. But if we plug in a negative here, it would turn the whole thing positive. Over here, if I plug in a positive number, the top will be negative, the bottom will be positive, so we end up getting a negative. So this means increasing, decreasing. So something that's increasing and decreasing means we have a maximum point. So you would say we have a max point at x equals 0, and f of x is increasing from negative infinity to 0 and decreasing from 0 to infinity. And we'll revisit this one. I'll clean it up a bit, and then we'll do it for a review. Okay, so that's D9, and our last standard for this unit.